Thank you that you're here with us in today's webinar. The event is organized by the online master degree in solar energy engineering. Our talk today will be on the assessment of cooling effectiveness in power yields of a multi-orientational BIPV facade of a high-rise building in a hot and arid region, the Octagonal Tower, by our speaker today, Micheal Riyad, who is the CEO of MRFS Power Building Contracting, as well as a recent graduate for our master degree. The duration of the webinar is 50 minutes, and you are welcome to ask any questions you have at the end of the talk. We will have a small Q&A session after Micheal Riyad finishes with his presentation. I would like to also give a very small introduction on our program. The Solar Energy Engineering is an online and part-time Master of Science degree, fully taught in English. It's a collaboration of 14 years between the University of Freiburg and Fraunhofer Institute for Solar Energy Systems in Germany. Our students and alumni are full-time employees located globally. In addition to the master degree, we also offer certificates of advanced studies, which last for 6 months. As you can see here, these are the certificates that we offer. You're welcome to check them out in the websites that I have here below, or in the email shown, which I will share with you in the chat box. Any questions you have before we start the presentation? Perfect. If not, then I will give the floor now to Micheal to start his talk. Micheal,
thank you so much. Yeah, thank you so much, Yasmin, and thank you for all the attendees. It's a pleasure to come again and give a talk to the university where I studied for like almost 4.5 years for the master degree in solar energy engineering. And it's a pleasure to be with all of you today. I wish you all good evening or good afternoon or good morning, depending on your time zone, because as you know, the sun is moving, so it's a different timing. And yes. For that, I will start my talk today about assessment of cooling effectiveness in power yields of a multi-orientational BIPV facade in a high-rise building in a hot and arid region, and the project name is the Octagonal Tower. Okay, so in the opening, I will start to just discuss about sun, and I will present my tie, which have this lovely sun, and this tie, it's branded CAS Solar for 2023, and it's a gift actually from Professor Dr. Kazmersky, Lawrence Kazmersky of the NREL, National Renewable Energy Laboratories in the United States, and he's the one of the team who started the famous NREL cell efficiency charts from 1977. I met him in person during the previous conference in Dubai, and this shows that how generations can interact in gathering or international gathering in the solar to share their interest in the research and development of solar energy. As we can see here in the NREL charts, that throughout the last 2 decades, there is a huge improvement in the cell efficiencies for all applications and all cell technologies. Some technologies started new, and some technologies also are no longer available in the market. And this gives us the indication that the science of solar energy is fast moving. And in University of Freiburg, it's a good chance to study solar energy in cooperation with Fraunhofer Institute for Solar Energy. And it gives us the state of the art in the solar energy research And this gives us also all the required skills and information to start a real research. Okay, so this talk today I presented in the IEEE MENA Solar Conference in Dubai 2023, along with another talk in building integrated photovoltaic. And both talks I present posters and I give a talk in the conference. And both talks are part of my master thesis, my methodology of the master thesis, which I assess in a real test setup, some of the parameters affecting the temperature losses and degradation for BIPV testing setup, and also another case which I did detailed simulation for orientations of high-rise building, and I checked the different orientational behaviors. So going to our talk about the Octagonal Tower, I will start with motivation. I will start with, after that, followed by introduction to the Octagonal Tower, then PV-Syst inputs, PV-Syst project settings, inputs and results of irradiance and efficiency, temperature assessment, power output results, and then conclusion. So in motivation, we know that building is development everywhere, and integrating PV modules in buildings, this known as building integrated photovoltaics, BIPV, is one of the promising solutions for energy problems in the recent years. This includes electric energy generation at the prosumer's level of smart grids, which is generation inside the same consuming place. When applied in energy efficient building, this will result to a balance between energy requirements and generation. And this is known as net or near zero energy building, NZEB. The most limiting factor of BIPV practical application is the high temperature losses due to the different mounting conditions of BIPV modules compared to BAPV building applied photovoltaic. And this is a major problem in the hot regions. This reduces the service life of BIPV modules, making it unfeasible option. The orientational temperature behavior of BIPV facades and the cooling effectiveness will be presented in this study. So this project, the introduction for the tower, it's a cooling simulation project for a multi-orientational high-rise building with 8 facades. It's an imaginary project located at Dubai in DEWA R&D Center. Okay, and this DEWA R&D Center is a part of Mohammed bin Rashid Al Maktoum Solar Park. And I assume that I will build there a tower, and I did all the simulation to this tower. Okay, it consists of 75 floors with BIPV modules above a 20-meter height podium. This location provides minimal far shading because the land is almost flat, and only near surface shading will be considered in this simulation. All simulations have been carried using PV-Syst 7.3 version. In this figure, we can see the Octagonal Tower, and if we have a close look for it, we will see, like if we look here, it's 3 floors. All these black lines represented, or black areas are represent the opaque areas, which I consider PV modules in it. And each floor have 2 modules installed vertically above each others. The others are glass areas, which is not considered in this simulation. And in this figure, we can see the 8 orientations of the Octagonal Tower. When discussing the PV-Syst inputs, we'll start by the project locale, and the project locale is in Bab al-Bahr, Bab al-Shams, Dubai, UAE, at latitude 24.77 degree north, longitude 55.37 degree east, and altitude 112 meter above sea level. The time zone is UTC +4. Meteorological inputs, I use Meteonorm 8.1 for the years 1991 to 2007 with saturation 50% synthetic hours. And as we can see here, this monthly meteo data from the PVSys for the project site. And we can see that here we have yearly 2041 kilowatt hour per meter square. And this almost a good irradiance level. The project settings, I consider two projects for the settings concerning the site-dependent design parameters, and I compare the both together. I assume that we have the Octagonal Tower in hot region and the Octagonal Tower 2 in the same locale with comparatively lower operating temperature. PV system, I have 600 PV module, each 410 watt, and one inverter, each of 200 kilowatt AC for each facade orientation. So all the 8 orientations having the same configuration. The inverter loading ratio was 1.23. And in this table, we can see the inputs and the global effective irradiance extracted from PVSys. Here we can see the full tower. All facades are vertically, and this is the 8 orientations. The total number of modules, 4,800 module with nominal power 1,968 kilowatt peak, and with 8 inverters, and the inverter nominal power 1,600 kilowatt AC. We can see that the average global effective irradiance is 745 kilowatt hour per meter square per year. And this represented as an average like 79.32% compared to the south only at vertical position. Here we can see each of the 8 orientation and rank it out as per the irradiance value. And luckily we find that the south, which is known as the best orientation for normal PV modules in the normal solar fields. In facades, we find in this position, southeast have 4.4% extra than the south, and southwest have 3.5% more than the south. And also interestingly, we find that the north have 34.2% compared to the south. This chart shows, or this figure shows the shading 3D scene of PVSys. And if we have a closer look, we find that each facade orientation, each color represents one string, and each string have 20 modules connected in series, and for each, and this considered for simulating the electric detailed simulation for the shading. Simulation cases, I did 12 simulation cases for the full tower to study the cooling effect in the system output power and module temperature and temperature losses and performance ratios. Then we find that I use different module mounting conditions in the PVSys detailed temperature losses to represent different ventilation conditions. For example, integrated with fully insulated back, semi-integrated with air duct behind, free-mounted modules with air circulation, customized mounting conditions also for that. And this considering the thermal loss factor, which contains the thermal losses, which contains constant loss factor and wind loss factor. Here we can see in this figure some of the cases integrated with fully insulated bag and the values represented to each case, and semi-integrated and free-mounted, and then customized modules, customized mounting modules. In the simulation cases, some cases, the PV module specification have been modified to reduce the temperature losses by altering the thermal parameters. This happened or by changing the reference conditions to represent cooling cases. So for example of that, I changed the STC temperature from 25 degree to 50 degree, assuming that the module at 50 degree with cooling for the full tower. We find here the simulation cases, the 12 simulation cases for the full tower. We have the project name, the Octagonal Tower and the Octagonal Tower 2. And then we have the PV project settings for the site-dependent design parameters. And we have the parameters for the operating conditions. So we have the temperatures. This Octagonal Tower is in relatively hot area, which is the same location. And Octagonal Tower 2 in a cold area. And all this happened for the modules at different mounting conditions. And here we find the cases of mounting conditions and the values of thermal loss factor, which contains the constant loss factor and the wind loss factor, okay, for each case. And here the PV module inputs, and we have here the module name, and if it's modified or not modified. Only I did few modifications at the last 3 cases, and the modified parameters for temperature coefficient or the temperature reference at STC or the alpha, which is the thermal absorption factor. This is the values, and then this is the results. We find the power to grid in megawatt hour per year. We find the first case have 1,247 megawatt hour per year, and the 12th case with the full cooling or the full cooling that I can simulate in the program with having our power output ejected to the grid 1,420. We can see that the performance ratio was 80.04% for the system, and it reached 91.13%. And the concerning losses in this study, we have the irradiance level loss and the temperature loss. The irradiance losses was minus 2.46%, and this is reduced to minus 2.05%. And the temperature losses, which is the main study of this case, minus 8.43%, and this is reduced significantly by cooling to minus 2.21%. If we see the results of Octagonal Tower 1 and the Octagonal Tower 2, we find that both have the same results in each case with the same mounting condition, with the same module. And this is due that the PVsyst consider the METEO data from the location, the hourly METEO data. And this simulated cases is not considered in the results. So this inputs of temperature, site-dependent temperature, is not considered by the program at all. So the results are actually similar. Okay, so we have case 1, which represents the worst case, fully insulated module with the highest temperature losses, and case 12, which represents good ventilation with good cooling for the module, and this gives us the highest power output. I did detailed study for each orientation simulated separately to get the exact figures for each orientation for case 1 and case 12. If we check here the monthly irradiance, and this chart actually is not in the publication, I didn't show in the conference, but it's mentioned in my thesis as well. So here we find the 8 orientation for each month, and we can see that the average in-plane irradiance is almost uniform across the year, and this gives good potential for BIPV facades. Here we can see the ambient temperature, which is one of the main causes of temperature losses. And interestingly, we find that the north and northeast and northwest receive higher monthly in-plane irradiance than south, southeast, and southwest orientations, and this has happened during May, June, and July. So the north have more than the south in May, June, and July, and as well as northeast and northwest. Okay, so temperature assessment for each individual orientation. And this was the reason also I did individual assessment for each orientation, because PVsyst gives the hourly the hourly temperature as an average of all the system. Hourly module temperature as an average of all the system. So when you simulate only one orientation, you get the temperature for each hour for this orientation. So I did the separate systems, and then I combined the results in one graph. So, and I studied the days which have the maximum temperature, hourly temperature in the year. So luckily, in a summer day of 20 May, we have east, west, northeast, and northwest having the highest value in the year. And if you can see here, this I indicated in red, and the blue values are the maximum values in the same day. This for case 1, and for case 12, after cooling, we will find that the temperature have dropped, and it's very close to the ambient. And you can see also that the temperature scale I increased to give to make it visible. But when we discuss the temperature or the requirement for cooling, it's necessary to check the difference between the module temperature and the ambient temperature in the same hour. So if we minus the array temperature from the ambient temperature, we'll have these results in the same day of 20 May. And we find that the maximum values, for example, here, east have 34.6, west 34.7, but the northeast in the same day have the highest value in the year, 27.6%. After cooling, this difference reduced. But here also I increase the scale significantly. This is from 0 to 10, while the other one from 0 to 45 degrees. So to make it visible, okay. And luckily we have the pattern looks like a spider for the winter, for the summer days. And interesting findings that the cooling requirements is limited to 3 orientations simultaneously. You have here 3 orientations and here only 3 orientations, and no cooling is required in the mid hours of the days in the summer. North and south orientations are very close to ambient with almost 5 degrees above the ambient, and the cooling will not add any valuable gains. In winter days, the shape is look like that, and we find that the temperature difference between array temperature and the ambient temperature is higher. And we find, for example, the southwest have 43 degrees above the ambient in this day, in the winter, in the day of 24 January. And the pattern looks like turtle for almost all the winter days. And cooling is in winter is much more complicated due to the need to cool a minimum of 4 orientations simultaneously. Here, if you want to cool the facade, you need to cool 4 together in the same time, in the same hour. North, northeast, and northwest orientation do not require any cooling due to the smaller difference, which is almost 5 degrees above the ambient. When checking the power output results, here's the power results of case 1 without any cooling, and here is after maximum cooling. So I make this heat map to show each orientation, power output in each month, and the total. You can find here total power gained through the months. And if you can see that there is a good average, this gives us potential that the BIPV facades for such configuration can be good to cover part of the requirement of the building, power requirement for the building. So year 1 or this year we have 1,247 megawatt hour without cooling. With cooling, it reached 1,420. And we can see also here the contribution for each facade orientation to the total power output. So for example, we have here the maximum contributions coming from southeast without cooling, and the least is for the north, 5.3%. While after cooling, we will have almost same with slight changes. Okay, so I also grouped the facade orientations south group, which is south, southeast, southwest, which are almost 49% of the power coming from this. Then east and west, we have 28.5%, and then the north group, which is north and northwest, northeast, 22.5% from the total power. We can find that the total power gains is 172.8 megawatt hour by cooling, and this is represented 13.87% above the case without cooling. Luckily, we can see also here that the north, northeast, northwest have higher power output compared to south, southeast, and southwest during May, June, and July. Okay, so when we check the temperature losses in a detailed diagram like this heat map, we find each orientation monthly value from the total losses of the tower. And we have the total losses in case one without cooling, it's 120.7 megawatt hour, while after cooling, it's reduced to 33.8 megawatt hour. If we check the total monthly power gain due to cooling, this minus case 12 with the highest power minus case 1, and this is resulted gains. And here we can find that the maximum gain happened to southwest, which is 17.3% from the total, followed by southeast 17.3, and the least gain is north 3.9%. And this figure shows the same values as the percentages from the same. Okay, so based on that, we can arrange the facade orientations with higher ranks of cooling gains in descending order like that. Southwest is the highest gain, followed by southeast, then south, then west 15%, east 14.5%. And the least gains are northwest, northeast, and north, reaching 3.9%. So in conclusion, different operating temperatures for each facade orientation is a case of BIPV. The cooling gains in power output can reach up to 13.87% for the combined 8 orientations together. Southeast and southwest have higher power output than south. Then north, northeast, northwest have higher power output than south, southeast, and southwest during May, June, and July. Facade orientations with higher ranks of cooling gains are southwest, southeast, and south, while the least are north, northeast, and northwest. Cooling requirements in winter days are much more complicated than summer days, and more cooling is required in midday hours for winter days than summer days. Some orientations do not require cooling in summer, like north and south, while others in winter, like north, northeast, and northwest. The published papers in that conference, I have 2 papers, and as I informed, it's part of my master thesis methodology, and it's published by IEEE, and you can find it in IEEE Explore, and this is the reference numbers. And thank you so much, and I would be very happy to answer any question.
Yeah, thank you very much, Micheal, for your presentation and for sharing it with us. Here we have actually a question that Mahziar Paraspor has left for, I think it was in slide 14. He asked, what factors are essential to consider to reduce energy loss in high-rise buildings?
Okay, let me get this slide 14. So can you please repeat again the question? Yeah.
What factors are essential to consider to reduce energy loss in high-rise building?
Great. So mainly the factors is to reduce energy losses that we need to make the geometry of the building to reduce the shading losses. So this is factor number one. Second factor is to maintain proper ventilation. And proper ventilation means proper uniform ventilation for the modules in hot regions as well as moderate climate regions. And this will increase the power gains or the power output, and also it will reduce stresses in the material due to temperatures or spikes in temperature happening to the modules. And this extra temperature happening to the modules will cause fast degradation in some technologies. Like, for example, I prove in my other publication that CIGS have 3 times degradation than crystalline silicon, which was recommended to be used in BIPV because it had less temperature coefficient, while crystalline silicon modules have high temperature coefficient for the losses, temperature losses, but it's the material is more stable or more proven to be long-lasting than the CIGS. So the selection of material as well is more important. Then there are a lot of other regulations required, but one of the limiting factors is the degradation, which will cause the BIPV installation unfeasible as a building element. And as we can know that the building life is from 50 to 100 years, while the PV modules in BIPV will have only warranty up to 10 years. So it's also good item to be considered.
Yes. Mazia, do you have any follow-up question? If not, then Mr. Khao, you had a question, please. Mr. Gomez da Costa, do you have a question to share with us?
Oh, I'm sorry. I thought you were calling somebody else.
No, sorry.
Right. Micheal, thank you for the presentation. I did not understand something.
Yeah.
Is the cooling only done by how to say this? Is the cooling only done by the wind or the air passage between the PV cells and the building? Or is there an extra type of cooling?
Yes, actually in this study, I simulate that I have customized cooling condition, like active and passive cooling combined together. But the cooling I want to assess in this study only was to check if I cool the module, what will be the results of simulation. But how cooling is done, it's a different techniques. You have passive techniques and active techniques. And this was the core research of my master thesis. Okay. One of the passive techniques to make double skin ventilated facade.
Okay, sorry, please.
Yeah, it's okay. Yeah, so
just an observation.
Techniques have been tested in another modules in different conditions, using cold water, using air circulation, and a lot of other combined techniques, PCM, and how to cool the modules. It's another research. But
yes.
I assume in this study, if I have cooled the modules, what will be the power output? What is the temperature losses? And if I have the module with worst case, without any ventilation, without anything, what is the losses? So I compare to check the orientational gains or the gains for each orientation from cooling or from simulating a maximum cooling condition. And I did this by alteration in the project, in the PV system parameters. There is no option for cooling, only you have option for module mounting condition, to have it insulated or semi-insulated.
Exactly.
Or you can do this, but I did another tricks in the software to assume that I have also an active cooling.
Yes, because I was thinking if the module, if the silicon temperature changes due to the cooling, that's also going to influence the power conversion, so the efficiency and so on. One thing I thought was that, especially if the building is very high, the air that goes, let's say the example in which you have the PV structure far away from the building. So the air going in between is going to be colder in the bottom, but when it gets to the top, it's going to be already much high temperature. So the parameters for cooling are going to be different. I'm not sure if PVC is going to that detail, but maybe something to consider, I guess.
Yes, actually, this is an actual case of non-uniform cooling of double skin facades. And this also proven in different researches or different tests that the natural ventilation is not uniform cooling.
Yep.
If you have double skin facade. And also you have the chimney effect happening. All hot air will go up. So if you didn't extract it fast, then you have the cooling effect for the lower modules is much higher than the upper modules. And this is the case. But in PVCs, this is not considered in this simulation case. This simulation case, I assume different mounting condition and different module reaction to the thermal gains. So this is why I alterate if I make uniform cooling by active cooling. For example, if we use cold air or cold water, or we did absorption for the heat gains by PCM. What will be the, if I maintain this case, what will be the power output? So the technique, how it's done, in reality, it's totally different, and it's still a matter of research and practical research. Okay, but what will be the outputs if I have cooling, uniform cooling? This is the core of this simulation.
Thank you.
Welcome.
Here we also have a question from Pierluigi. He thanked you for the presentation, and he asked, which are the main obstacles in your experience to make a BIPV facade competitive for the real market in UAE region, and why only a few solar facades, between brackets, experience and costs? But the first question is the main obstacles in your experience to make a BIPV facade competitive in UAE.
Yeah. Thank you, Dr. Pierluigi, and happy that you attend. Dr. Pierluigi is one of the top researchers in SUPSI. So they're related to the task 15, the regulations of BIPV applications. And the limitations in UAE or in hot climatic regions is to find first, you need to find a BIPV module that it's approved as a building element. So BIPV is the use of PV modules as a double function. So it's a PV generator plus a building element. So it should fulfill all the regulations and requirements for PV module as well as a building element. Example for that, it should have approval from fire department or civil defense, as well as fulfilling the building codes for wind loads, for mechanical integrity, for stability, as well as the glare, because the traffic and all that. So if the PV module give different glare, this would be or high glare or high reflection. This will make problems with drivers in the roads as well as aeroplanes. So a lot of regulations to fulfill this and this, and you need also to get it approved by the electricity provider or the grid operator. So along all of that, in addition to the stakeholders of the building, the owners of the building, architects, also limiting factors. But the main concern or the main selling point for PV as a BIPV module is that you are going to maintain net or near zero energy in the building. So to make self-generation for the building and to have like an active facade. But how to guarantee this if you have high temperature losses and fast degradation? This is the main concern, and this was the main topic of my research in my master's thesis. Until now, there are some facades here in UAE and in Dubai, in the Expo, have BIPV, but they're also installed few years back, and some of them are not performing now. One of the test setups, I have proven in my second publication that the CIGS have 3 times degradation than the silicon, and I've proven also that the degradation is different by orientation. So the fast degradation is mainly the limiting factor, and fast degradation coming from temperature losses or high temperature and different cooling condition compared to the normal PV modules. And this need additional research to be implemented successfully in one of the sun-rich regions like UAE.
Yes. Do you have any follow-up questions, Pierluigi?
No, not really, apart from thanking you for organizing the workshop and Micheal for the presentation. Maybe just quickly concerning maybe costs, if any analysis on cost competitiveness, or if you also joined this technical and energy analysis with some cost effectiveness studies. I mean, you also assumed some active measures for cooling or similar cooling strategies, I would say. So if you also considered the impact in terms of extra or over cost, so if the economic aspect is related to your investigation, essentially. Thank you.
Yeah, thank you so much. Actually, cooling of PV modules is considered as 2 parts: passive cooling or active cooling. Passive cooling, you don't have any equipment like fans, like pumps, like cooling equipments. Active, you have fans, you have cooling equipments. So how to do this? You can also have passive, like we're using PCM, phase change material, to absorb the heat gains. So implementing this in building require a lot of research. And this is why the core output of my master thesis was the design of BIPV cooling testing unit. And this is like have some intellectual rights. This research, we will do the cooling simulation and check what is the gains by each method for different technologies. Okay, so in this simulation, which is the topic of today, the cost is not measured. I just assume that if I have full cooling, what is the power output, what is the temperature losses for each orientation, and is that good, like 17.7% for southwest, or it's not feasible, like 3.9% for the north. So this was the core of this research, but the actual cost analysis, it's a subject of different future researches as well.
Perfect, thank you. We also here have a question from Vicent. He is asking why it was important to change the STC conditions and how did that affect the final results?
Yes. Okay, so I changed the STC condition assuming that I have a cooling. So I like alter the module losses, or I assume that, for example, if the module have the highest efficiency at STC condition 25 degree, then I assume that at 50 degree with cooling, it will achieve the same. So I just minus the 25 degree from the STC condition, and this gives positive results and negative results. But luckily, because I also changed the temperature coefficient, the losses of temperature coefficient, the reaction of the module is different. So when you change these parameters, and I did actually numerous simulations, but the 12 cases shows this, that wherever you change the STC conditions, this means that you have more efficient module that can be able to produce at 50 degrees, same as 25 degrees. But this 50 degree is not 50 degree. This 50 degree with cooling, it will be similar to 25 degree. So it's actually a tricks that I try to make it in PVsyst because there is no software that consider the cooling or active cooling. So I assume that if I have a module with cooling, it can produce at 50 degrees similar to 25 degrees.
Do you have any follow-up question, Vicent, or is it's clear? I believe should be clear. Do you have any other questions, any of you as well? Here, Mohammed Abbasi is also a student with us. He's thanking you for sharing your invaluable study, and he asked whether you could please discuss a little bit about how you design your simulation, parameters choosing, etc. You could also.
Yes,
it's a big question.
Yeah, it's actually a longer procedure. So first I decided to check the orientations. So typically a building have 4 orientations. Some buildings have 6, some buildings have 8, or circular buildings or like that. So I just find that the previous studies, they have only main 4 orientations. So sub orientations like southeast, southwest, northeast, northwest, I need to check it. And luckily, when we did this simulation, we find that the southeast and southwest have higher irradiance and higher power output than south for buildings. When you assume a facade with vertical PV modules installed in it. Okay, then I follow to simulate the modules. Then I try to remove any clashes between the modules and each other and the building by adjusting the spacing between the modules together and all this stuff. Okay, and I choose properly the modules that if you put 2 modules above each other can make a normal floor height of a standard building here. Okay, but the main case that I tried also to check the height effect, and I take the tower above a podium to avoid any near shading. Okay, so this spatial geometry I did for this project to only analyze the temperature gains or the temperature losses and power gains for each orientation with pure effect, without far shading, with only near self shading, which if we check in the results, the self shading or the shading losses, it's not shared here in the PVsyst reports, is very small value. So the geometry itself, I make it to assume this case, and then I try to play with the parameters, the project settings, and I find no effect for the project settings. That if you assume the temperature, operating temperature, I can also share here again. This one. Okay. So here, if we change the site-dependent design parameters, it have different results. Okay, from case to case. But in the same, if you assume that the project in cold area, I find that the Meteo files result is taken into consideration by the program, and no difference in the results. So this simulation technique, or this assumption that I assume that the project in a cold site, whereas the locale of the project is fixed, the Meteo files is taken from the local. So this assumption. Then I play with the module parameters for the thermal losses, and then the system configuration of the modules. I tried to have similar modules in all facades at the same time, and also same configuration for each orientation, and same inverter for each orientation. And then this is a combined results. That's it. So this take like months to get these results for different cases, but this is the final results. Yeah.
Thank you. Do you have any follow-up questions, Mohammed, or any of you as well, if you have any further questions? I also have a few questions, although less technical ones. As you mentioned before, today's talk focuses on your master thesis. And I would like to ask if you can share with us insights into your experience during the thesis writing process, and what were your highlights during it as well, and how you found the project with DEWA and so on.
Okay, so actually, I need to share my experience first with the program. So the program, I spent it like 4.5 years in total. I have some breaks, and I took the full curriculum because I have a structural engineering background. So it was hard for me to study microelectronics and all this stuff, the behavior of electrons and what is the photons and all this stuff. I cannot visualize at that time because I have visualized only buildings. So, and then I tried to gain all this experience from the program, from the professors in the University of Freiburg, and also by visiting Fraunhofer Institute and the labs, and it was very very rich experience for me. Then when I decided to make my master's thesis, I decided to make practical thing, but I cannot go to Germany because my work here and family in Dubai. So I try to find a good research institute. So I find here the biggest electric company, DEWA, Dubai Electricity and Water Authority, and it's known as the 5th smart grid in the world. They have huge solar park, and the research institute or center, R&D center, it's a part of Mohammed bin Rashid Solar Park. I approached them after a few months of negotiations. I find a chance for internship there. And thanks to them all and to my supervisors, I attended there part-time for a long period. Then I start to see the issues happening in the field and why the losses happening and what that. And I start to get to check what is the test setups they have for the buildings or BIPV. And I did some proposals for like designing experimental setups, new experimental setups. And when I find that the parameters all that require to be tested from all publications, all the publications and the existing test setups in DEWA or in any other place in the world is more complicated, I focus only to design a testing unit, cooling testing unit. And this is the main core of my thesis, but it's still need to be constructed and tested. I also, in my methodology, I try to analyze the existing testing setups output for different technologies, and I add to it to have a building with 8 orientation very high to represent the scale of buildings here, and to see the effect of BIPV with cooling or without cooling. What is the effect, orientational behavior for each orientation? Okay, so this was a practical thesis, and I gained a lot of experience by being subject to test setups. The same can be done in the module scale or cell technologies in very advanced level in Fraunhofer, but I cannot attend in Fraunhofer. That's why I try to find another practical thesis in Dubai. This is why. Okay, that's it. So it was long journey to find the topic, to register the topic, to get it accepted by the university, and to start working in it until writing the topic.
Yeah.
Yes.
Also, your company is focuses on BIPV as well. So that was also that's also leading to my question on how did your experience at the master program as well as with the master thesis contributed to your professional career and also to your growth in your company? Yeah,
actually, my company is in construction field, and it's 10 years old company, and we did construction for different projects for in here in Dubai or in UAE in general. Okay, BIPV cases was very limited in my work, and this is my future business plan. But to resource and find the proper modules that are approved by authorities, and now the authority regulations are to be implemented, unified code and all the stuff is in advanced stage. It's about to be announced in Dubai to have a uniform code for BIPV. Then after that, we get the things that is approved and use it in the market. So for example, I have here samples of BIPV modules. Okay, and you can see it can generate electricity in night indoor. So different colors, different modules. Indoor as well. Yes, it's here. The light, the LED light, but this efficiency is still less. And here, this is also a module that reflecting, but also it can generate power. Okay, and there are a lot of other options, but my main concern before using all these modules to make something durable, to make something that will not have degradation, and also feasible to be used economically in the building, and it shall fulfill all the regulations. And the regulations here are quite organized, quite complicated to make sure for the building safety, and this all delay the application in commercial scale. Until now, only some few projects have BIPV, few projects like in Expo, which are temporary buildings, 6 months or more constructed. They have a lot of new technologies, but it is not the case of a permanent building. So this is why implementing the case of BIPV in UAE in general and Dubai, because it's advanced case, is still slow, but it's going to be there.
Yeah, as you said, the BIPV field will keep on increasing, will keep on getting better, and with the right research, with the right regulations, as you mentioned, it's the future basically for buildings or like construction, building constructions, from now on. One last question that I have. I hope if there are any technical questions, you can still ask them, of course, in the chat or live. But one last question I have is, what advice would you have for prospective applicants to the program? Since you studied the program, you're an alumnus already. What kind of advice would you give them?
Yes, actually, I would like to advise the potential students or researchers in solar field. This field is moving very fast. It's the science is developing in very fast way. And whenever I attend conferences, I find new technologies. Things are hidden in labs, might be in commercial use after a few months or few years. So new technologies, new patents are also there. So it's fast moving, and it's not only for buildings. So in solar fields, in vehicles, BIPV, in agriculture, APV or agro photovoltaic, and the technology of tracking, and it's a lot of things moving very fast. So when you ride the train early, you reach early. So I just advise to have continuous education. For me, till now, after graduation, every day I find something new. So it's moving very fast. So I encourage the potential students and researchers go on, but it's not easy. It's not easy. If you like this science only, then you can resist and give your energy to it and the workload enough, so you will know everything in an organized method from organized teaching method by the professional professors in University of Freiburg and Fraunhofer ISE. It was very interesting for me. Also, I am from different engineering background, but when you are from any background and you go into solar, you will find the common application suitable to your experience. So for me, I'm in the structural building background, so I find that BIPV is common for me. So I learn PV and I combined with buildings. If you are from agriculture, then you can do it with agri-photovoltaic. If you are from chemical or physics specialist, then you can work in the processing of PV modules, finding new techniques, finding new manufacturing process to make it more efficient, to make it more economic. So everyone have a chance, but you should like it. Yeah.
Thank you very much for your advice. We highly appreciate it. Gustavo Rocha here also asked a question. He's also a recent graduate from a program. He said he asked, between the first contact with the research center until you got your topic accepted by the university, how long did it take?
Yeah, okay.
We can have this as our last question.
Yeah. Actually, because I was the first one to approach this research center, it was a hard journey for me to find the legal configuration or legal documentation to enter there, the R&D center, because all R&D centers have the confidentiality of the research. So to find the suitable way to enter there, it's take long time. Then to find the approval take another time. Then once I enter there, I start to find the current research topics and the issues happening in the or not the issues, I mean the problems of solar fields in hot climatic region and the degradation and all this stuff. Okay, so I start to find something suitable for me. So it takes time to find the exact topic. Also, it takes time for me to find, to check all literature related to this topic in buildings or in solar fields, and to find the research problem to present it as a main research issue or subject for the thesis. So it takes for me months, like 6 months to find the opportunity. Then after registration, I take 6 months also to submit the thesis. So as per regulations, you have 6 months, yes. Then before that, you need to prepare yourself. It take another 6 months.
Yeah, definitely. Perfect. Yeah, thank you again very much for all your valuable insights, like answering everyone's questions, as well as sharing your like a year basically, or like more than a year's time of work that you had on your thesis. Thank you very much for sharing it with us. And thank you as well to everyone that joined us.